So in this video, I'm going to explain about that what is AVL tree. So AVL tree, before coming to the AVL tree, first I will explain you that binary tree. First I will explain you the binary tree, and second I will going to explain the binary search tree. So binary tree is having single property is that a node is having at most two children, means 0 children, 1 children and 2 children. So this is called binary tree. Now coming to the binary search tree. Binary search tree having the one extra property. One is that a node is having that 0, 1 and 2 children. Another property is that one extra property is saying that the left children is less than equal to parent and right children is greater than parent. Right children is greater than parent. So this is the binary search tree property and this is the binary tree property. Now coming to the AVL tree. Coming to the AVL tree. AVL tree is having one extra property. See, this is also binary tree as well as binary search tree. So AVL tree is a binary tree and binary search tree. It means that the both property will come. Means a node is having 0, 1 and 2 children. Then after the left children is less than equal to parent and right children is greater than parent. Right children is greater than parent. Two property come. Third property is saying that balance factor. Third extra property is that balance factor. So in AVL tree, each and every node, remember that each and every node is each and every node balance factor in range is 0, minus 1 and 1. So for every node the balance factor range should be 0, minus 1 and 1. So this is the extra property of the AVL binary search tree, and because of that reason the AVL tree is called height balancing binary search tree. Because of this balance factor, the AVL tree is also called strictly balanced binary search tree. Strictly balanced binary search tree it is called. Right? And what is coming to the balance factor? I have said that each and every node is maintaining balance factor and that range should be 0, minus 1 and 1. Then what is the balance factor? So balance factor is nothing but a height of left subtree minus height of the right subtree. Balance factor is nothing but a height of the left subtree minus height of the right subtree. And just now I have said that each and every node have balance factor range is 0, minus 1 and 1. Now one more thing is that why we were using the AVL tree, what's the use of the AVL tree, why the AVL tree came, right? So in the binary search tree, what was the problem with the binary search tree? Binary search tree is having the problem in the worst case. In the worst case we can say that if the input is increasing order, if the input is increasing order as well as if the input is in decreasing order. In this situation increasing order and decreasing order situation, suppose this is given that 1, 2, 3, 4 and 5, right? Suppose 6 also. So here same thing in decreasing order, 6, 5, 4, 3 and 2, 1. Right? So in this situation, if you are going to construct a binary search tree, and then will perform the searching, the time complexity will high. The time complexity will high in this situation, and this is nothing but a worst case time complexity of a binary search tree. Reason is that suppose if I am going to construct binary search tree, what is a binary search tree? Binary search tree is having one property is that at most 2 children, another is that the left children should be less than equal to and right children should be greater than, right? So if I am going to construct for this increasing order, I will get the binary search tree is like that: 1, 2 and 3, 4 always is greater value. So it always come to the right side. Similar like that 6 also will come. So look at that how the binary search tree is constructing. Suppose here 1000 to the power 1000 to the power 1000 node is there, then what will be the size of the binary search tree? And this will going to generate a problem. This will going to generate a problem if you are going to store this data in the memory. So suppose I'm taking the example of the any company. In company, what happened, they are storing employee data, right? So if they will going to use binary search tree or technique to store the data, what happened that there is a single height is coming, means they are continuously coming there, means they are increasing the height, and that's tough to store as well as for the searching time also. If you want to search the 6, if you want to search 6, what happened that you are coming from root to leaf here, and that's nothing but a, you are checking each and every node, because here there is no concept to the left side. You are not going in the left side, you are not going to the left side, because always you are coming to the right side, and because of that reason the time complexity will be the order of n. Means if it is you have a 1000 to the power 1000 node, means the time complexity will be the 1000 to the power 1000 order of that much time will take. Similar like that for the decreasing order, what happened that 6 will come, then 5 will come, 4 will come, 3 come, 2, like that you are coming to the completely left side, and this is called left skewed. This is called left skewed, this is called right skewed. Means if it is the increasing order item is given and decreasing order item given, that it is going to form a skewed, and that is the problem with the binary search tree, because the searching time will increase for this situation. If it is your tree become a skewed binary search tree, then the time complexity become the order of n, and that is very high. And as well as it's also going to problem for this insertion, right? So this was the problem with the binary search tree. This is skewed problem was the binary search tree. Then AVL binary search tree came. Because of that, AVL binary search tree is having one extra property, is that balance factor, and that's maintaining that the at most one, means 0, -1 and 1, that range should be the 0, -1, 1. So it will going to help you to perform searching in a AVL binary search tree. It will take only order of log n, only order of log n. Either you have an increasing order, either you have a decreasing order. Whatever the situation will come, AVL tree always the searching time is order of log n, and that's the reason AVL tree introduced. So I hope you understood what is the AVL tree and why AVL tree is introduced. Now we'll see that some problem with the AVL tree also, and how it resolved. For that we perform some rotation. We'll see in that. Before going to the rotation part, first I will explain you that how do you calculate the balance factor for each and every node, right? We have how we have to calculate the balance factor for each and every node. So suppose this is a given binary search tree. Assuming that suppose I am creating one binary search tree, then I will construct, that's for better understanding. So I have just created like this is 60 and this is a binary search tree, so the lesser value always come in the left part. So this is 55 I am taking, this is 30, this is 25, and here is 65, this is 70, and this is 62. Right? Now this is a binary search tree. This is a binary search tree. But what is saying the balance factor? Balance factor, what balance factor it is? Balance factor is saying that the height of the left subtree minus height of the right subtree. So if I am going to calculate balance factor for the 60, if I am going to calculate balance factor for the 60, it means that this is a left subtree and this is the right subtree. Right? So what is the height of this? What is the height of this left subtree? So height of this left subtree is, what is that? Height is 1, and we have to also, so there is a formula that height of the left subtree plus 1 is the height of this 60, right? So total height of this 60 is nothing but a 2 minus, if I am assuming that suppose this is the height of the subtree, if I am taking that 1 and height of the subtree is what? 1 here. So 1 minus 1 is 0. This is a one way. Another way is saying that how we calculate the height. Height formula is that the height of this tree plus 1, because here I am taking that complete left subtree. This is the formula of calculation of the height of the binary search tree or binary tree, right? So the here is nothing but a 2 minus 2, you will get 0. So similar like here for 50, if I am calculate for the 50, what will be the balance factor for the 50? So their subtree is 30 and their left subtree is 30 and right subtree is 25. Sorry, it's not 25. I'll take that of 57, because I'm following the binary search tree property. No? Right subtree is always, right children always be greater than. So this is the 57. So what is the balance factor for 55? So for that 1 minus 1, here is 1 minus 1, because here is one height and for this also one height. So 1 minus 1 is 0, right? For this one 65 also 1 minus 1 is 0. So like that we'll calculate the balance factor of a node. Look at that here in this diagram. For this diagram, what I'm doing here, I started from the 100. I started for the 100. So for 100 is that if I'm saying that these are the left subtree. These are the left subtree, right? And this is the right subtree, right? So if I calculate the height of the left subtree, what is the height? Always take the maximum height. So height of the left subtree is, this is the one line, this is another line, this is another line. This is the maximum path. So that's called the height of the left subtree of the 100 is 3 and right subtree is 2. So 3 minus 2 is what? 1. I am getting 1. Now coming to the 50. Now I'll come to the 50, and 50's height if you calculate, then left subtree, 50 is having only single left children, but right children having three right children. So 1 minus, if I check that the height of the right subtree is 75 and 85, this is having the highest path, and also 65 is also highest path, so both is having 2. So the balance factor will be 1 minus 2 equal to minus 1, right? Similar like the 25. For coming to the 25, there is no left children, no right children. It means that the height is, for left subtree height is 0, for right subtree height is 0. So balance factor is 0. For 70, height of the left subtree is 1 and height of the right subtree is 1. So 1 minus 1, 0. Right? Coming to the 150. 150, height of the left subtree is 1 and height of the right subtree is 1. So 1 minus 1, 0. And for the 125, there is no left children, no right children. It means that height of the left subtree is 0 and height of the right subtree is 0. So 0 minus 0, 0. Similar like that for 175, no left subtree, no right subtree. So height is 0. So this is the way of calculation of balance factor. Now we'll see that the problem with the AVL binary search tree, because while they performing the insertion and maintaining the balance factor, while performing the insertion and the searching as well as the deletion, what happen is that while performing maintaining the balance factor or maintaining the binary search tree to be balanced, so we have to while doing this we'll face some problems. So we'll see that what are the problem we'll face. So suppose if I'm going to insert this 30, 20 and 10, what happened is that first I'm going to insert 30. 30 I have inserted. Then 20 came. 20 is the greater, 20 is the smaller than 30, because following the binary search tree property means lesser will come to the left and greater will come to the right. So 20 will come. So 20 I have inserted in the left part. Then 30 came. 30 is also inserted in the 10 come. 10 is also inserted in the left part. Now we'll see that here I came here, right? 30, 20 and 10 I have inserted. Now I am going to calculate balance factor for each and every node. So if I am calculating the balance factor for the 10 is not having left children and right children, so its balance factor will be the 0. Right? Similar like that for 20, if I calculate, then the balance factor will be the this is the left children is there, so there is a 1 minus right children not there, so 0. right? So what is the balance factor for 20 is 1. For 30, height of the left subtree is 2, and for the right it is nothing, so 0. 2 minus 0 is 2. So look at that, this is violating the property. This is violating the property. Then wherever the node, whichever the node is violating the AVL tree property, what we will going to do there, from that node onwards, we'll check that what problem it is. So this is the left children, right? This is the left children. So this problem is called LL. This problem is LL. We can say that LL rotation. So this is called LL rotation. This is called LL rotation. So for this tree, how we perform that rotation, so we'll get that valid AVL binary search tree, because this is not a valid AVL binary search tree, because this is not balanced. So for this reason, if we get this type of situation LL, if you get that LL situation, then we have to perform rotation is like a right rotation, and from middle node. See, I am going to perform from middle node, right? So what we will get that after this right rotation. So if you get that situation like the LL problem, then you have to perform that right rotation, and that too from the middle node. That too from the middle node. So the 20 will come up. The 20 will come up, and 30 will go to the right. 30 will go to the right, because I have performed this right rotation. I have performed here right rotation, right? So 20 will come up and 30 will goes down, and 10 is as it is. I will complete. So this is called LL problem. This is called LL problem. Coming to the another one. Suppose they have given like a 10 given, so 10 have been started. 20 is the greater than 10, so 20 will come in the right side. 30 is the greater than 20, so 30 will come to the right side, right? So if you observe that this is the RR problem. This is the RR problem. So if it is the RR problem, from the middle onwards, look at that, from the middle node to perform here left rotation. Left rotation. We will perform left rotation. So what happened here? This 20 will goes up and 10 will come to the left part. Here, if it is RR situation will come. If it is RR situation come, then from the mid we have to perform left rotation, right? Then after what we will get that 20 will be the root and 10 become the left children and 30 is the right children, right? Now coming to the another situation. Suppose there is a 30 first, we have to insert first 30, then 10 and then 20. Suppose this situation will come. So I have inserted 30 and 10 is the lesser than 30, so 10 will become the left children and 20 is the greater than 10. 20, when inserting the 20, first we'll check the 30, is 20 less than, yes. Coming to the left part, left part, then I came to the 10, then 20 is less than 10 or greater than 10. If it is 10, then will be the right children, right? So now I am going to calculate the balance factor for every node. So for 20, 0 minus 0, then you will get that 0. For 10 is 0 minus 1, because there is no left children, so 0, and right children 1, so 0 minus 1, you will get value is what? Minus 1. For the 30 left children is 2 and right children not there, so 0, it means that 2. So this is also violating the property. So from inserted element, always we have to calculate we have to start calculating balance factor from the new inserted node. So here I have inserted 20 at last, and then I have calculated balance factor from 20 to 30. From 20 to 30, first I have calculated a 20 is balance factor, then 30 is balance factor, sorry 10 and then 30. So we have to calculate minimum 3 node, because we are performing the rotation on the 3 node. So minimum 3 node we have to calculate the balance factor. So I have calculated balance factor, and this 30's node is violating the AVL tree property. Now from 30 onwards, we'll check that what type of rotation it is. So here is that left children and here is the right children, right? So this violation is LR. This problem was LR. This problem is LR. Suppose this type of situation will come. So here you can see that you have seen that if it is LL problem, then you perform that right rotation. If it is RR problem, you are performing left rotation. But then what will you do with if it is both problem will come, means LR problem will come. For that situation, first LR is na, then you have to first perform that LL rotation. First you have perform left rotation, first you have to perform left rotation, and then you perform that right rotation, right? So two rotation you have to perform. So both rotation, just now I've explained, both you will do. But first see, this is the LR na, this is the LR. So first you have to perform left rotation, then you perform the right rotation. So for that situation, what we will going to do? So here what will I going to do? So for this one, for left and for right, what I'm doing, I was doing rotation from the middle node. I was doing rotation for the middle node. But here I'm going to perform rotation from the this last node. From here I will going to perform that left rotation. So for that I will first perform the left rotation. So 20 will goes up, 20 will goes up, and 10 will come down, 10 will come down, right? And 20 will goes up, and the 10 will come to the down, right? And 30 is still there, 30 is there only. So if you observe now, this is become a what? This is become a LL, this is become a LL. If it is LL this is here I perform the left rotation, this is I perform left. If it is LL, if it is LL situation, here I have explained, if it is LL situation, then what will you do? You perform right rotation, and that too from middle node, that too from the middle node. So this was the first step, and this is the second step, and after the second step we'll get that balanced one, and this is 30 and this is 10, this is 30 and 10. So this is called LR problem. Same for that this situation. Now 10 will come. I will calculate the balance factor. Suppose there is a single node, so that will be the 0. Then 30 will come. Then 30 inserted in the right side. Then 20 come. 20 inserted in the left side. Now start calculating the balance factor. So balance factor for the 20 is 0. For 30 is 1 minus 0, because there is no right subtree, so the value is 1. And for this one 10, for left is 0 and right is 2, right is 2, so you will get the 2. So here again violating the property. Now from 10 you onwards you start that whatever problem it is. So here is that right and this is the left. So what will you do here? For this one you have to perform first right rotation, and then after you perform left rotation, right? And right rotation, how you perform? You have to perform between this two node, this two node you have to perform, right? So if you are going to perform here right rotation here first, then you will get it what? 20 will goes up and 30 will come to the right part, and 30 will come to the right part, and 10 is as it is, 10 is as it is. So if you see, look at that, this is the RR rotation, this is nothing but RR rotation. If it is RR rotation, what you are doing? You are performing left rotation. So for the left rotation, what you are doing? You are coming from the middle value, so what will you get? 20 will get, then this left side 10 and this 30, right? So this is the RR rotation, this is RR rotation. So this is all about the left LL problem, RR problem, LR problem, and RL problem. So these are the, this is the also called the type of the rotation in the AVL tree. So there are 4 type of the rotation. That's the LL. One is that RR, another is that LR, and next one is that RL. So for LL rotation, what you are doing? That you are performing right rotation. For the RR, what you are doing? You are performing left rotation. For LR, what you are doing? You are performing left plus right rotation. Both you are performing. For RR, you are performing right as well as left rotation. Both you are performing. So these are the situation you will get while inserting the element in the AVL tree. If you construct the AVL tree, you will face this type of the rotation problem. This type of the problem you face. So for balancing or for maintaining the AVL tree property, we have to perform this type of rotation. So that's why I have explained here for the better understanding. Now I will explain you the some application of the AVL tree where you are going to use AVL binary search tree. So here is the AVL binary search tree, and all the 3 point I have mentioned, all these are saying only one thing is that searching is important. Only is searching is important. Reason is that the AVL binary search is height balanced binary search tree, and because of that reason the time complexity of searching in a AVL tree is order of log n. Order of log n. Reason is saying that why? Because this tree is having left children as well as right children, and left will be the lesser than and right will be the greater than, as well as it's a height balance, and that height balance is maintained by balance factor, and that range is 0, 1 and -1. Because of that situation you will always get that balanced AVL binary search tree, and the reason is that time complexity will be the order of log n, and in this situation you never get skewed binary search tree. Because of AVL binary search tree you never get skewed one, because you are maintaining height, right? And AVL binary search tree is strictly following the balance factor concepts, means a strictly balanced binary search tree. So here if observe, if I read that first statement, what is saying that the database application where insertion and deletion are less common but frequent data lookup are necessary, means we were, if I creating the database for any industry and any college and any e-commerce site, sorry, business, anywhere, you are creating database only once, you are inserting the data only once, deleting the data only once, but the searching you are frequently doing, so for that situation, you can use AVL binary search tree, because that will going to take less time, right? You can also use this AVL binary tree in the game with plot lines. There you can use, there also you perform searching. And here also say that in real life example, in business sector what you are doing, that where it is necessary to keep the record in employee, where that work there in shifted range, means they have a shifting work. For that time you are going to easily check that which employee is having which shift, so that of the searching you are frequently doing. So for that situation you can use the AVL binary search tree. So this is the application of the AVL binary search tree. So that's all about that AVL tree, and why we have used AVL tree, and what is the what is the time complexity of the searching in the AVL binary search tree, and where we have to use. So that's all about the AVL binary search tree. Thank you for watching my video.